Hi guys, here's my summary of the main points about the number e. Why is it important and what we can do with it. So that's the number e. Basically, it was named by and after Leonhard Euler, a Swiss mathematician back in the 18th century. But actually it was first suggested by John Napier, who you know from logarithms. He made logarithms, but he also suggested this idea when he was investigating some compound interest stuff, calculations. But it was actually first properly suggested and explained or discovered by Jacob Bernoulli. There's lots of interesting history there. These are very interesting guys. If you're bored one day, I'd chase up some of that history and learn a bit more. Anyway, there are a few definitions of this, and I'm not going to show you how and why these exist, but basically this is the first definition that Napier and Bernoulli came up with and Euler synthesized. And you can change that into this if you're good with your limits. And then we can also make it into an infinite series based on this. So this is kind of the 18th century definition. This is the 19th, 20th century definition. So I'm not going to show you how they work or where they come from. But I will just quickly show you this, that actually by putting a few numbers in Excel, I can show you that that formula actually does work. But you can see it takes a long time to actually get close to the right answer. I've got to get up to 10 million there. X has got to approach infinity. Well, 10 million, I'm not quite there. If I use this other formula, I get there a bit quicker, but it's 1/10,000,000th there. With the new formula, with this infinite series formula, you get 1 plus 1 plus, so it's 1 on x factorial, let's just say x. And now it does say x, and so 0 factorial is 1, so that's 1 and 1. And that's 1 factorial is 1, 2 factorial is 2, 3 factorial is 6, etc. And you keep going down and you get very close to 0 very quickly. If you add up all those, you get very close to e very quickly, within 13 steps there, although because of these are all zeros, probably within 10 steps you get it right. Okay, so that's what e is. It's this magic number. But it's not magic. It's useful and practical. So probably the most useful thing about it is we can make exponential functions like this one. This is e to the power x. Now a couple of things, like every other exponential function, goes through the point 0, 1. Well, every other exponential function in this format, something to the power x, will go through 0, 1, but it goes through 1e and 2e squared and 3e cubed and -1 e to the -1 or 1 on e, and -3 1 on e cubed. So that shows you how this works. So finding, if you're given x, to find y is pretty easy. So if you're given y and you want to find x, you've got to take the logs. So the base over here becomes the base here. Now because this is a popular number and we use it so often, we're going to call log to base e ln. And ln stands for natural log. I think it's French for log natural, but natural log. So I say ln or lin, and some people say lon and other things, but there we go. If you look at your calculator, you'll either have a button that says e to the power x and with a ln above it, or you'll have ln with a e to the power x above it, showing you that these are inverses of each other. which we'll come back to in about 10 seconds. So if 5 equals e to the x, then x equals ln 5. Log to base e of 5, so ln 5. And check that in your calculator. Same if 8 equals e to the 2x, then 2x equals ln 8, and x equals ln 8 divided by 2. Check it in your calculator, get 1.04. Just repeat the same thing with 2 because we're going to use this later. So if 2 equals e to the x, then x equals ln 2. So if I replace this x with this x, you can see that 2 equals e to the ln 2. That's going to be an important thing later. Okay, so ln is just log to base e. So all the laws you've learned before apply. Here's a whole list of the laws you learned before, and probably 2 new ones. And this is just what I told you before with the button. E to the ln x equals x, and ln of e to the x equals x, because they're inverses. They undo what the other one does. Okay, so there we go. All right, keep going. There's e to the power x again. We're going to zoom in on this section. I'm going to put a tangent in there. What you see there, that the gradient of this tangent, well, if we just go from here to here, do rise over run, you get 1 over 1. So the gradient there is 1. The y-intercept and the y-coordinate there is also 1. And actually, if we look at a bunch of other points, what we notice is everywhere that the y value and the gradient, or the derivative at that point, are the same. And that's why, that's the most special thing, and that's the most important application of this number e. So if you've got the function y equals e to the x, the derivative is the same as the y value. The slope is the same as the y coordinate. The derivative is the same as the y value for a given value of x. In other words, if f of x is e to the x, then the derivative is also e to the x. We can write that shorthand. The derivative of e to the x equals e to the x. And by using the chain rule, you guys could do stuff like that. Derivative of e to the 2x is 2 e to the 2x. Derivative of the inside times derivative of the outside. And same here. So that's why the graph of y equals e to the x is really important. And this little fact is a really helpful thing, because you get other graphs that are not e to the x. Maybe it's 2 to the x. But just remember, a few minutes ago I told you 2 is e to the ln 2. So 2 to the power x is e to the ln 2 to the power x, which is e to the ln 2 times x. So just like what we've done over here on the left, when we differentiate this, we use this chain rule just the same. And we get ln 2 times 2 to the power x, or ln 2 times e to the ln 2 to the x, which will be 2 to the x. Okay, so that's a really powerful fact about this graph, this function, that we're going to apply to other functions, and other functions that don't have the same characteristic, we can differentiate them by transforming them. We'll talk a lot more about that. Other applications for this are, of course, in complex numbers, and some of you may come across this Euler's equation, which is the most beautiful equation ever, because it links up two transcendental numbers with an imaginary number, and the powerful operation and the two powerful numbers, unity and nothing, and it equates them all. It can also, the letter E can also help, but number E can also help us with exponential growth and decay as a kind of alluded to a few seconds ago. It's actually really important in probability because a lot of things can be modeled using E, and because the probability of all the different outcomes has to add up to 1, and a lot of these become asymptotic, and so that's why E's involved in a lot of these. The prime example is with these bell-shaped curves, which are normal distributions, and they get this shape as a function that involves E. So, and you can't do it without E. So it has a lot of applications in complex numbers, which has applications in electrical engineering and other things. It has a lot of applications in finance, but also biology and geology and ecology, and in probability, which has wide applications. Here's just a fun fact. I'll race through really quickly. The area under the curve of y equals 1 over x from 1 to e is 1. The area from e to e squared is also 1. If you look at that, those 5 areas are all 1. That's interesting but not useful. But you can see that e comes up a lot, and just randomly you'll find it popping up all over the place. So the main thing to remember is E is just a number, but it's a special number. It's about 2.718, but it comes from these two formulas. Most important application is that the derivative is exactly the same as the y value. Okay, I hope this was helpful, and there's lots of other videos out there about it here. You can go watch a few, or better, try some questions and see what you can work out. Bye.